Okay, let's start. We have the last talk of this session. Please welcome Nian from International Center for Theoretical Physics, Asia Pacific, who will talk about low-dimensional areas, quantum gravity theories, and applications.
Okay. Thank you very much. Let me start by thanking the organizers for giving me the opportunity to share our recent work. Although the title is Low-Dimensional AdS Safety Quantum Gravity, but actually my primary interest is still high-dimensional AdS black holes. But if we go to near horizon region, usually we have some low-dimensional AdS. And it turns out, based on the recent year studies, it turns out it's convenient to discuss some quantum gravity fluctuations in the near horizon region. And although it's not full quantum gravity, but it's helpful to capture some low temperature quantum gravity effect, and it can give us some very interesting new ideas and can possibly resolve some previous long-standing problems. And this talk is based on some of our recent 3 papers and some work in progress. So let's start by considering such questions. Of course, I guess all the people in the room are interested in quantum gravity and interested in how to possibly find some fingerprints of quantum gravity. Well, in the literature, up to, I think, 5 years ago, when people talk about quantum gravity, they usually talk about, I would call it UV quantum gravity. So they introduce some high curvature terms in the Einstein-Hilbert action, usually suppressed by some Planck scale, and compute some quantities by quantizing that theory as an effective field theory. Okay? But why do we need to go to Planck scale? Have you ever thought about that problem? Well, we usually don't ask that until very recently. My answer is to that question is why do we really need Planck scale to have some quantum gravity effect? Well, my answer is probably not. But why previously we require this Planck scale? Because we always have competition between quantum fluctuations and thermal fluctuations. And we want quantum fluctuations to win. Once quantum fluctuations win, we can possibly have some quantum effects instead of thermal effects, right? But usually we are at relatively high temperature, okay? So that's why we require the energy scale to Planck scale. Then we can have definitely very strong quantum fluctuations. Probably we can never go to so high energy scale. So an easy way, once we realize that we don't really want very strong quantum fluctuation, we just need a quantum fluctuation to win in this competition, maybe we can suppress its opponent, okay? So that means we probably can go to very low temperature. We suppress thermal fluctuation. We don't need to amplify the quantum fluctuation, just to manifest quantum fluctuation by suppressing thermal fluctuation, okay? So once we realize that idea, we just consider very low temperature, okay? And then in that very low temperature limit, I think conceptually all the physical observables should be averaged over these quantum fluctuations. And I would call it infrared quantum gravity compared to what in the literature, what people usually do, what they do in quantum gravity, I would call it UV quantum gravity. And that's the first question. And second question, how possibly can we observe quantum gravity effects? Well, I think probably in the next few decades or in the next century or few centuries, I think the only technically available signatures are just gravitational waves and black hole image. By black hole image, I mean photon rings, okay? There probably cannot be some smoking gun effect, which only quantum gravity can have, but classical gravity cannot have. I think the only possibility is we try to use some theoretical quantum gravity models to compute some quantum gravity corrections to gravitational wave and photon ring, black hole image, those signals, and see some difference, okay? I think that's to me, that's the only possible way to detect a quantum gravity effect in the next few decades, okay? But the question is, do real black holes in our universe, do they really have low temperature? Well, surprisingly, the answer is yes, okay? Surprisingly, all the supermassive black holes in the center of most galaxies, including our Milky Way, they are very close to extremality, okay? So that means that they have relatively low temperature. So we should not neglect their infrared quantum gravity fluctuations. And a useful tool is, of course, AdS-CFT correspondence. I know there are many great experts on AdS-CFT in the audience, but maybe to some students or beginners. So now it's a big area, but the first prototype was probably proposed by Mendocino in the end of November, actually, 1997. That's a duality between not a field theory and gravity. That's a usual misconception. That's actually a duality between boundary field theory and string theory, bulk string theory. And it's a duality between 4D field theory and 10D string theory. That's one thing. Another thing is after Mendocino proposal, people, including Gubser, Klebanov, Polyakov, and Witten, they made the proposal more quantitative, more precise. Okay, now we have this dictionary. Another misconception is usually people say it's a duality between quantum boundary field theory and classical bulk gravity theory. I think that's usual misconception because precisely speaking, it's a duality between quantum theory and quantum theory. Why we usually take classical bulk gravity and gives us a very good approximation because we take a large Hooft coupling and a large n limit. So according to the dictionary, you can see once we take a large n limit, the Newton's constant is very small. That means we probably can neglect quantum gravity effect, okay? Once we take large n limit, okay, then effectively the string length can be sent to 0. So we neglect the stringy correction, okay? So that means we take both large Hooft coupling and large n limit, we get a very good approximation as classical gravity theory, okay? But precise speaking, it's not classical gravity theory in the bulk. It should be quantum gravity theory or even string theory. So in this talk, we're more focusing on this large, but not strictly infinity n limit. So that means we are going to consider some quantum gravity corrections, but we fix lambda. So in this talk, we neglect the stringy corrections. Again, as I said, my primary interest is a high-dimensional black hole. And this low-dimensional AdS, quantum gravity, only play a role in the near horizon region. Then we can probably do a simple classification of high-dimensional black holes. Well, it's not a complete classification, but let's take a look at most usually often seen in the literature that these common black holes. First, the Schwarzschild black hole. It doesn't matter asymptotic flat or asymptotic AdS. So they don't have very good near extremal limit because the temperature of Schwarzschild black hole is inversely proportional to its mass. To have strictly zero temperature, we need infinite mass limit. So it's not very physical. And it doesn't have a good separation between near horizon throat and the far from horizon region, okay? So this technique it doesn't work very well for Schwarzschild black hole. The nice example we consider is a near extremal Reissner-Nordström black hole. So it has nice near horizon AdS to throat. We can turn on some AdS to Jackiw-Teitelboim gravity theory, which is dual to 1D Schwarzian theory. Actually, there are more than that. We can consider, let's say, D1, D5 near extremal black holes. We go to near horizon. We're going to have some BTZ region. And I think not many people pay attention to this. I ask because I think, again, this is not new, but in recent years, Kohler and Jensen, they revisit this BTZ and it's a dual theory. Some Liouville, we will show that, briefly review that towards the end of the talk. Some Liouville-like theory, okay? I think this theory plays the role of Schwarzian theory. So it's sort of like JT Schwarzian duality, but lifted one dimension higher, okay? I think we can use this Liouville-like theory, recently revisited by Colin Jensen, to do quantum correction, what we use Schwarzian theory to do, okay? But to be honest, not many people pay attention or realize this possibility. I even asked Jensen himself a few weeks ago. He said that he didn't consider this possibility. Anyway, we'll see that, how to use that. And the most physical one, I would say, is extreme or near extreme curve black hole. Because we now have gravitational wave signals. And the gravitational wave signals show that all the physical black holes in our universe, they're all curved black holes, no charge, okay? And in particular, as I said, supermassive black holes, surprisingly, they have very low temperature, okay? And the near horizon geometry was actually discussed by Professor Wei Song and Straminger and their collaborators in 2008. And also in recent years, revisited by Professor Rangamani and his collaborators, Straminger and his collaborators, and Professor Panozayas and the collaborators. Well, to me, the near horizon, what they call NHEK geometry, to me, it's a warped AdS3, non-trivially fibered on an interval, okay? So eventually, we want to consider that. We want to introduce quantum correction to this near horizon geometry. My point of view, my starting point is I want to study the warped AdS3 gravity and its dual 2D theory, sort of like another generalization of JT Schwarzian duality. I think once we have that, I probably can compute the quantum correction to the real black hole and compute, in particular, the gravitational wave and the photon ring, and compare to the real observation, okay? But, okay, we also need our experimentalist colleagues to improve the precision, okay? But as theorists, that's what we can do, okay? This is outline my talk. So, as I said, as the title suggested, it's about theory and application. But based on the current available theories, we only have JT theory and Schwarzian theory. We're going to discuss 3 applications based on my 3 recent papers with my collaborators. And another theory, the AdS3 and the dual 2D theory. Again, it's not new, but recently revisited by Colin Jensen. We can use Colin Jensen, their theory, to introduce quantum correction to near horizon D1, D5 black hole, also the BDZ quasar modes. But some work in progress, but we're going to mention that briefly. About theory side, we are working on, as I said, warped AdS3 and a new dual 2D theory, and some summary and a prospect towards the end. Okay, we don't have, I think we have to agree, we don't have a full consistent quantum gravity yet, okay? But suppose we have. Well, what can we do? Well, formally, we can write down the partition function, okay? It's going to be a path integral over the metric or graviton and some matter field, okay? And we consider a saddle point of the metric and consider some fluctuation around that saddle point, okay? And the most physical quantity we can compute is some correlation function of those fluctuations, okay? And in addition, we can also compute the matter field on this fluctuating background, but we quantum average. We compute the correlation function matter field on this fluctuating background, okay? Of course, this is just formally. In practice, there are many open issues like, naive quantization of gravity. It's not randomizable, okay? So some issues about randomization, and another issue is suppose we take the background to be some space-time around black hole singularity. How to deal with the black hole singularity is another issue, okay? Yes? Right. Right, sort of, we start with some saddle point, which is, as I said, my saddle point is some high-dimensional black hole, either asymptotic flat or asymptotic AdS. But we usually go to the near horizon region, and we assume, yes, I think we have some saddle point in mind. It's not full quantum gravity. Eventually, we will go to IR and consider some fluctuation around IR fixed point. Right. Yeah, eventually it's effective field theory. I would say the recent development probably was initiated by the work by Polchinski and his student, and also by Marcina Sanford and Yang. They revisited the Jekyll-Teitelbaum gravity theory, which is a 2D gravity theory with a 1D boundary. Okay. So if we integrate out the bulk dilaton field, okay, also we plug in the bulk equation motion, we arrive at this 1D theory, okay? And surprisingly, the main part of this action is something we are familiar with from conformal field theory. It's a Schwarzian derivative, okay? So what does it mean? On the 1D, we only have time, okay? Suppose the O time is t, and we have to, this action actually is integral over all the possible new time, new parameterization. That means the O time is t, new time is any function of t, okay? It's not necessarily small, but we can do perturbation theory. That means the new time f of t can be the O time plus some small quantity, okay? But this is only perturbation theory. It's not necessarily small, okay? And we're also left with the boundary dilaton field. In principle, it can be also a function, not a constant. But let me recall in Madison, Sanford, and Young's paper, in the paper, literally, they said that let's assume this boundary dilaton to be a constant, okay? And then we can put this constant outside this integral of the action, and combine with the 2D Newton's constant, we define a new variable c, okay? Actually, this c carries the dimension of length. That means it's really like EFT, because this C inverse just gives us a new energy scale. I would say the new energy scale, the meaning of the new energy scale is at which the quantum fluctuation will become dominant, okay? When the temperature or some energy, our real energy or frequency of some wave is bigger than 1 over c, we probably can neglect these infrared quantum fluctuations. But when the temperature or some frequency of some wave is approaching or even smaller than this new energy scale C inverse, I would say we cannot neglect quantum fluctuation. We have to include them. We have to average over all the quantum fluctuations, okay? That's the famous Schwarzian theory, okay? We arrive at the famous Schwarzian theory. And in Marcel Sanford and Young's their paper, they compute that in perturbation theory, they compute that reparametrization, the small epsilon, as I said, but that's only tree-level result. Later, a Korean group, they compute this two-point function of epsilon up to 1 loop. Okay. In principle, you just treat the Schwarzian theory as a new quantum field theory. Not very familiar quantum field theory, but just we can use standard Feynman integral, Feynman rules to compute up to any loops as you like. Okay. Anyway, so far we have a tree level and a 1 loop result for this reparametrization mode, and also the matter field. Also in Madison, Stanford, and Young's paper, they compute the two-point function of the matter field up to only to the tree level. But in principle, we can include higher loops. Okay. And then let me remind you, we said we don't have quantum gravity yet, but if we have quantum gravity, what do we want to compute? Of course, the correlation function of the fluctuation. And sort of this epsilon two-point function plays the role of the correlation function of fluctuations. Okay. And if we have full quantum gravity, we want to compute matter field correlation functions. And this matter field correlation function within Schwarzian theory sort of play the role of matter field correlation if we have a full quantum gravity, okay? And this is what I said. So we start with the AdS 2 disk, and we can consider some fluctuation in the bulk, but the AdS 2 has a problem. We can always find a new change of coordinates. We can find a new coordinates such that the bulk metric will, after fluctuation, we can bring it back to the strict AdS2, okay? But we have some price to pay. The price to pay is the boundary will become wiggling, will become our curly, okay? And all the dynamics is captured only in the boundary, okay? Still, there are different perspectives. we can view the bulk to be fixed AdS2. All the dynamics is captured in the boundary. But we can also consider the boundary is smooth. All the fluctuations are in the bulk metric. Okay, these are two different but equivalent perspectives. Okay, so in the next slide we'll see Elias Utraj in their famous 2020 paper. They use the first perspective, but in last year, my paper with my students, we sort of use the equivalent but different but second perspective. Okay. So again, our recent work, not just us, some other people's work, including some people's work in the audience. I think we were inspired by 2020's work by Elias and Turaji. So after that, Marcina Sanford's Young's work in 2016, it took a few years for people to really make it useful, okay? Because previously, they only considered AdS2 safety 1 correspondence. It was nice, but it's a toy model, okay? We can only make it less toy, only by including this AdS2 GAD gravity, embedding it into some near horizon region of some high dimensional AdS black hole to make it less toy, okay? Okay, this idea is not new or not fancy, but I think the 2020 paper by Elias Utraj is really a nice example to make it work, to solve some still long-standing, but not the big paradox, big information paradox. There's some small, I would call it a radiation paradox, formed by Priestley and other people in 1990s. So they consider a near-extremal iron black hole, okay? And it's well known in the literature, the entropy of near-extremal iron black hole has its form. Previously, we only have first two terms, okay? It was well known in the gravity community. Also, with some collaborators, we derive the first two terms using AdS-FT, okay? So the near-extremal iron black hole entropy is just equal to the extremal black hole entropy plus the term linear in temperature, okay? And then using the first law of thermodynamics, dm equals TdS, we integrate it, we get m, the near-extremal iron black hole's mass is equal to extremal iron black hole's mass plus the term quadratic in temperature, okay? Just those first two terms will lead a paradox. Why? Because once the iron black hole starts radiating Hawking particles, well, according to Page's argument, it can only radiate massless particles. And what massless particles do we have in standard model? Only photon, graviton, and neutrino, if you call neutrino massless, okay? But all of them, they don't carry charge, okay? That means near-extremal iron black hole, once it starts radiating, it will reduce its mass, but it doesn't reduce its charge, okay? Originally, the m is slightly bigger than q, but once it starts radiating, m will approach q, okay? So that means that the second term, the first term doesn't have any temperature, it's extremal one, okay? But the second term is the energy available from a near-extremal iron black hole, available for the Hawking particles, okay? That's a maximal energy the Hawking particles can carry away from the near-extremal iron black hole, right? But it's a quadratic function in temperature. And we know that the Hawking radiation is almost a black body radiation, okay? So we can compute the average energy carried by one Hawking quantum. It's gonna be linear in temperature, okay? And then it's a primary school fact. For very low temperature, linear function is higher, is bigger than quadratic function, okay? Then it's paradox. Because the black hole has non-zero temperature. It wants to radiate, but it cannot afford even one single Hawking particle. One Hawking particle has bigger energy than the energy the black hole can provide, right? It's just stuck there, right? It wants to radiate, but it cannot radiate even a single Hawking particle. So what was a paradox for, I think, 30 years, okay? Okay, there are many proposals, but not satisfactory ones, okay? But once we consider the quantum correction, so Elias Turaji in their 2020 paper, they just, as I said, they include JT gravity fluctuation, essentially some Schwarze mode, in the near extreme, in the near horizon AdS2 part, okay? Compute the partition function, but it's not full quantum gravity partition function. It's like a effect. Formally, we write down the path integral for the quantum gravity, but we only evaluate the near horizon fluctuations. Far from horizon, let's assume it's to be classical. Okay, so that means that they only consider a subset of all the quantum gravity fluctuations. But turns out it's the most relevant one, most important one, and it's enough. Okay, and then they recompute the path, the black hole entropy. They get the third term, which is a quantum correction term. Then they use the first law of thermodynamics, dm equals TdS. They integrate this again. Then this log T term will give us a term linear in temperature. Then there is no paradox because it's the energy available by the black hole is not just a quadratic function in temperature. It's going to be linear function in temperature for very small temperature, but gradually become quadratic for still low temperature, but relatively high temperature. So it's a combination of linear function and quadratic function. So for very low temperature, both the energy available by the black hole and the Hawking particle, they both are linear function in temperature. So no obvious paradox, right? Anyway, I think it's nice work, and we were inspired by this work, but I think this is not the end of the story, but instead, I think it's the beginning of a big, big program, okay? Anyway, people are pushing in this direction, applying the similar ideas to solve some black hole problems, like recently people can compute the quantum corrected Gribble factor. Some work by Elias Pennington and their collaborators, and recently by Professor Pandazayas and some students. Also, this year, Professor Emperor from Barcelona, he computed quantum corrected absorption cross-section black holes using similar ideas, okay? But as I said, once we realize this idea, that is not the end of the story. Because AdS safety is mutual, we can use boundary theory to study black hole. We can also use bulk gravity theory to study the boundary theory, right? And once you realize this idea, you probably agree with me. I think starting from 1997 to now, almost 3 decades, I think we should revisit each and every single work of near-extremal AdS-CFT. So if you randomly take some work in the last 30 years, if they consider near-extremal AdS-CFT, 99.9% they don't consider quantum fluctuation in the bulk. They usually just consider classical gravity. And I'm sorry, but conceptually that's wrong. Conceptually that's wrong, period. Because it's not optional. You have to consider quantum fluctuation. Okay, you said, I don't have enough tool. But now I think we have some tools, okay? So as I said, I think that's a big program. And together with some collaborators, we are doing some work. But I think we don't exhaust all the possibility. I suggest someone in the audience probably can join us in considering these related questions. So as I said, we'll consider in this talk, we're going to briefly discuss 3 examples. So some strange metal, and some Wilson loop and its consequence on the super Yamiya's confinement, and some quasi-normal modes of black holes. And some ongoing work, again, including still Wilson loops, but we are going to consider 2 Wilson loops and relate to the Yamiya's mass gap, and some low temperature fluid gravity correspondence. So I recommend you to look at my student Cong Yue's poster. It's based on our almost finished ongoing work with student Cong Yue and Professor Pandazayas, and a famous E over S. We are computing quantum correction to E over S, and we have some preliminary results. Okay, let's move on to the first example. It's an application of AdS-CMT. Again, it's not our model, I would say. It was studied, I think, 15 years ago by the MIT group. So they want to study the strange metal. It's very important in condensed matter because strange metal is just the higher temperature phase of a high temperature superconductor, okay? Of course, we want to find a high temperature superconductor. Once you have a high temperature superconductor there, you do nothing. You just put it there, increase the temperature. Above the phase transition temperature, it will become a strange metal. So that's why it's very important in condensed matter. We should first understand strange metal, then possibly can find some new high temperature superconductors. And it's called strange metal because it has very weird behavior compared to normal metal. So the resistivity for very low temperature, it scales like linear in temperature. Ordinary metal doesn't have this scaling, okay? This is called DC resistivity. We also have AC conductivity, okay? It also has some weird scaling law, okay? So people try to answer, at least theoretically, to answer this strange behavior, strange metal. As I said, the MIT group more than 15 years ago, they have some proposal using AdS-473, and Professor Sashiev and the collaborators, they have some complex SYK model to describe the strange metal theoretically. So what we do is we took these two models. We don't invent new models. We took these two models, but they haven't considered quantum fluctuations. So let's include quantum fluctuations for low temperature, quantum gravity fluctuations, of course, and see if we can see some new features, okay? Again, once we have this idea, it's not hard. The fundamental tool we're using is still the Kubo formula, okay? The Kubo formula, this is Green's function, but on the 3D boundary theory. There is a connection between the near horizon AdS2 71 Green's function and the near boundary AdS4 73 Green's function. It's well known in the literature. So let's quantum average the near horizon AdS2 71 Green's function. Okay, everything is analytical. Okay, we can do everything analytical. Maybe some integral we cannot evaluate precisely analytically, but everything is without approximation, just analytically. Okay. Once we have this quantum averaged near horizon AdS2 71 Green's function, we can lift it to the boundary AdS4 73 Green's function. As I said, it's well known in the literature. And again, apply the Kubo formula, but the right-hand side is quantum averaged. By quantum averaging, I mean quantum averaging over the near horizon some JT gravity or Schwarzian modes, okay? Let's see the difference. So the blue line is a traditional metal, okay? Strange metal is, again, linear resistivity, should be linear in temperature. This is a red line, okay? What we proposed is just consider some strange metal, but we need a very delicate sample. So suppose this 1 over C, the C is a Schwarzian coupling, okay? Again, this 1 over C has energy scale, okay? And sometimes in the literature, it's called quantum temperature. Suppose for some strange metal, the quantum temperature is slightly above the transition temperature. So we still want to consider strange metal. We don't want to consider, or not yet, we don't yet consider the phase transition between strange metal and the superconductor, okay? We consider quantum temperature. Suppose some sample has quantum temperature slightly above the phase transition temperature, and then according to our computation, it's going to be bent. It's slightly bent, okay? It's not a strictly linear resistivity. It's slightly bent, either towards up or towards down. The right-hand side is we use MIT group's AdS-473 model. The right-hand side is we use Professor Sashiev and collaborators' complex SYK model, okay? That's for DC resistivity. For AC conductivity, we expected some scaling law, but it was very controversial, I would say, in the literature because different experimental groups, they found different alpha, ranging from 0.5 to 1, okay? So we plot our quantum corrected results. What we found is, first, we set temperature to be 0 from the very beginning, and we tune this frequency to be very small. Again, when this frequency times c is smaller than 1, then we see some clear deviation from the classical result. Okay, so we see it's not a single scaling, it's a range. So it's our guess. Okay, it's not proven, but our guess. Our guess is probably different experimental groups measure this curve, if our curve is right, measure our curve at different frequencies. Then they get different alpha. Then they conclude. But we would say it's not a fixed alpha. Okay, it's a range. Okay. Anyway, that's our theoretical result. And recently, we discussed with Professor Jingwu Ye. He's the Y in SYK. Okay. We discussed with him. He said, "Oh, strange metal. The theoretical challenge is it's really hard to find one single model to explain all the quantities just within one model." Okay. You can explain linear resistivity. You can explain optical conductivity. But he said the hardest part is specific heat. He said we probably expect a T log T as specific heat. Okay. Well, we just took our theoretical model, we fit with experimental data, okay? You see, it fits very well. We don't invent a new model, just everything within one model, okay? So then I would say it's another maybe advantage of this model of including quantum fluctuations, okay? So it's gonna be, it's not in our last year paper, it's gonna be presented in our recent new paper with Professor Ye, okay? Okay, that's the first example. Let's move on to the second example. Something related to quark confinement, also discussed by Professor Gang Yang in his previous talk. So it's a very well-known, long-standing problem of the Yang-Mills theory. And a related problem is even harder, is Yang-Mills mass gap problem. It's one of the millennium problems in mathematics, okay? Unsolved millennium problems. Simply speaking, I think the question is just to explain why we never observe a free quark, okay? Maybe indirectly in some quark-gluon plasma, but not in some exotic matter. We never observe a single free quark, okay? Well, the qualitative explanation is if we want to observe free quark, of course we should stretch quark and the quark pairs, okay? But once we stretch that, it's like it's gonna form some string, like QCD string, okay? And once the string accumulates enough energy, it's gonna create a new quark and quark pairs, okay? So we never, by stretching them, we never create a new free quark, always quark and quark pairs, okay? That's qualitative explanation. Quantitatively, we want to compute quark and quark pair, the potential between quark and quark pair. It should be a combination of Coulomb potential with the linear potential, okay? It's confirmed also in the lattice data, okay? And theoretically, how to compute that? Well, AdS-FT gives us a very useful tool. So we just compute the quantum average one Wilson loop expectation value, okay? But historically, I will show you that. Historically, Mendocino, after inventing AdS-FT, the first application he did was to compute one Wilson loop expectation value, but he couldn't reproduce the linear potential. Okay, the new ingredient we have is to include some quantum correction from the near horizon region. Hopefully, we can get something more. Okay, we'll see. And again, it was already defined in Professor Gang Yang's talk, but let me briefly review. The Wilson loop is a very nice operator in the sense that it's a gauge invariant, although it's non-local. And in principle, we can extract all the physical observables from the one Wilson loop, two Wilson loop, multi-Wilson loop correlation functions, okay? So we just consider a rectangular Wilson loop, put it on a boundary, okay? And in the time direction, it's infinitely long, okay? And we put a quark, anti-quark, some probe quarks with a separation L, okay? It's a finite distance, okay? And then according to AdS-FT, it's gonna span a minimal surface in the AdS space. It's similar to the RT formula. But I think RT was, they were inspired by this Wilson loop computation. And again, as I said, Malasina, after formulating his AdS-FT in November 1997, the first application he did himself was to compute one Wilson loop expectation value holographically. But actually, a Korean group posted the paper before Malasina. So it was 1998, March, and if you check their archive number, they are 98 March 03001 and 98 03002, okay? Anyway, these two groups, they compute and they agree with each other. So what they found is, first, the one Wilson loop expectation value. From field theory side, we know it's going to be at the leading order, exponential minus the t is the distance in the time direction times quark and quark potential. And holographically, it's at the leading order is proportional to exponential minus the area of the minimum surface given by the Nambu-Goldie action, okay? So you let these two sides equal, you can extract the quark and quark potential, and they only found Coulomb potential. Of course, it's not surprising. Of course, they should have Coulomb potential because it's AdS5 and the boundary theory is n equals 4 super Yang-Mills, which is superconformal. In a superconformal theory, you can never find a confinement, period, okay? So this result is right. But later, not that later, in the same month, let's say 1998 March, so Witten proposed, he said probably we should consider, in the bulk, we should have a black hole there. We have some temperature, although it's a trick. Eventually, they send temperature to 0. But as an intermediate step, they need to consider some black hole with a finite temperature in the bulk, okay? But we didn't do very precise quantitative computation. But some other groups, they just follow Witten's idea and did the computation. And indeed, they can find confining potential. But again, you have to put some finite temperature black hole in the bulk in the beginning. Maybe eventually send to 0. But how about we start with 0 temperature black hole in the beginning? Let's put a 0 temperature iron black hole in the bulk in the beginning. It's like deform the AdS5 or n equals 4 super Yang-Mills with some finite chemical potential. Eventually, we are going to send chemical potential to 0. But in this intermediate step, because we're going to have near horizon AdS2, quantum JT gravity fluctuation will play a role, okay? And then let's quantum average that effect. So this is the same idea, but technically we use slightly different technicality, okay? We write down the AdS2 metric in the near horizon region in this way using the light-cone coordinates, du, dv. The advantage of using light-cone coordinates is we can consider fluctuation by u will become a function f of u, v will become function f of v, okay? And still, it has only one term in the metric, du dv, okay? And this operator in front, in Malasina Young's paper, is called a bilocal operator because it depends on 2 points, u and v, okay? And we can compute this group of people, Mertens and the collaborators, they compute the quantum average of the bilocal operator. But once we have the quantum average of bilocal operator, sort of we have a quantum average of the AdS2 metric, right? And it's given by, actually it's a double integral, and this is a simplified version because it's extremal, okay? We only have one integral, but the integrand has 4 gamma functions. So it's still not simple. It's very hard to evaluate this analytically, but let's expand the integrand in large C because C introduced a new scale, right? Strictly infinite C corresponds to classical limit. We want to see some deviation from classical limit, right? Let's consider large but not infinite C, okay? And then the new thing, together with my students, the new thing is we want to glue the near horizon quantum average AdS2 smoothly to the AdS5 because again, like Eliasson and Turaci, we assume that far from the horizon or near the boundary, it's classical, okay? Let's assume that classical geometry is smoothly glued to the near horizon quantum average geometry, okay? And in the end, we found that close to the boundary metric will receive some quantum correction factor. And if we're expanding large C, the quantum correction factor starts with 1, but with some 1 over C corrections, okay? Let's use this as our new metric, compute the minimal surface, repeat what Madasina and the Korean group did in 1998. Let's see what we found. Well, that's what we found. We found the leading term is exactly the same as the result, but we have expansion. The leading expansion is 1 over C squared is a linear in air. So that's the Coulomb potential plus linear potential we're looking for, okay? So this is a numerical result. The green curve is just Coulomb potential, okay? The blue curve is, we plot just the first two terms in the expansion, and the red curve is that integral of 4 gamma functions without expansion, okay? So both the blue curve and the red curve, you see clearly some linear part of the potential, okay? And okay, we didn't say that in our paper, but recently I talked to some people working on real QCD. They told me that suppose we have linear potential, then the coefficient of the linear potential should also have some non-trivial scaling, if it makes sense. And the non-trivial scaling should be start with 1 over n squared. Many people on the QCD community, they discuss this 1 over n squared leading correction. For instance, by this paper by Greenside, okay? And indeed, we have this coefficient because C scales like n. It's known from SYK model or some JT-Schwarzian duality. So C scales like n. Also, it's because C is related to the 2D Newton's constant. And according to that, the 2D AdS-FD correspondence dictionary, we also know that the C scale like n. Then indeed, the coefficient of the linear potential scales like 1 over n squared. Okay? We didn't realize that, but turns out our result makes some sense. Okay? Yes. Right. You can understand in that way. From Schwarzian, yeah. You can also compute the correlation function in Schwarzian theory. Right, it's not just what we thought. It's also Mertens discussing the paper. They literally call it a quantum average metric. The new thing we invented just to glue this near horizon quantum average AdS2 metric to the near boundary region smoothly. Okay. Yeah. Yeah, we start with near horizon R rising another Schoen black hole in the bulk. It could be, in a few slides, we probably can see, it could be very small. You can view this as a regularization of AdS space, but we need a black hole at the first place to have near horizon AdS2. Without AdS2, we cannot turn on JT fluctuation. I think they also need to introduce a black hole in the beginning. Eventually, you probably can send the black hole to the temperature to 0, but you need to start with a finite black hole in the beginning, at the intermediate step, I think. Yeah, maybe it's related to your question. Again, our discussion is how to understand this result. I would say Witten and other people, what they did, let's say this is phase diagram of Subayamio's in this paper. Well, just qualitatively similar to QCD phase diagram. And for low temperature and chemical potential, it's a confined phase. For high temperature chemical potential, it's deconfined phase. And sitting at the origin, it's Engels force. It's super conformal. So if you sit at the origin, forget confinement. You don't have a confinement. You don't have a mass gap. You don't have those infrared behavior. But what they did, or Witten and other people, what they did historically, I would say they deform along the 0 chemical potential, but the finite temperature along this way. Eventually, you can push this back to origin, but you have to deform it first, okay? What we did is we deform at 0 temperature, but with finite chemical potential, deforming this way. Eventually, we can send it back to origin, but we need to deform it first, okay? And some people say, it's well known in the QCD or AdS QCD community, just finite temperature, you can never have confinement, okay? Because chemical potential itself is not enough. But actually, what we did is not just chemical potential. We use chemical potential to set up a stage. Because we need chemical potential to have near horizon AdS2. Then the quantum gravity fluctuation will play a role on that stage. Okay? The stage itself can never work. But on this stage, we have a new actor. That's a new ingredient, okay? And we also compute the circular Wilson loop. And we found, as Professor Gang Yang said, we found the area law, just quadratic, okay? And of course, it's obvious different from the constant. Constant is a classical AdS will give us just constant. Obvious, it's not constant, okay? As I said, you probably can view this as a regularization. Eventually, we can send this black hole to be very small, but it's a special thing about extremal iron black hole. It can be very small, or it can be very big, but both cases, it has zero temperature. That's why I think structured black hole is nice historically, but it played a role only in the textbook. I think in reality, we should forget structured black hole because iron black hole, because structured black hole I talked to many people, but many people, they have the intuition. They said, okay, the bigger the black hole is, the lower the temperature is. The smaller the black hole is, the higher the temperature is. I think that's wrong intuition because they have that intuition based on structured black hole. But if you talk extremal iron black hole, either big or small black hole, extremal iron black holes, they always have zero temperature. It has nothing, it's no direct relation with the black hole size. Okay? It's similar for Kerr black hole. Okay? Anyway, and some ongoing yes? This one. Oh, well, we have expansion. You can expand to higher terms, but they're going to be 1 over c cubed, 1 over c quartic, and so on. Also not linear. It's going to be cubic and quadratic, higher power. Yeah. Some people also complain that it's not a linear confinement, but my response is definitely there will be a range. We have linear potential dominates. So if you require I have linear potential to L2 approaching infinity, no, we don't have. But whether you ask it makes sense in reality, I don't know. It's just the feature of our model. Okay. Actually, I want to, yeah. Sure.
Yeah. So clearly, a very short distance is so I'm trying to understand if you have quarks with respect to maybe also kind of free.
Right.
Is this really a zero beta function theory, or what's going on?
It's not zero beta function because zero beta function is at the origin, sitting at the origin, no deformation. We deform it a little bit. We deform it a little bit, turn the JT fluctuation, and push it back to origin. It's not the same as you see it as the origin all the time, right? It's kind of regularization, but different from previous Witten and the company's deformation. Okay. I'm not saying this is a final answer. I'm just saying it could. It's crucial, but you can look at the chemical potential itself is not enough because the linear potential is independent of chemical potential. We need chemical potential because only when we have finite chemical potential, we have near horizon AdS2. As I said, chemical potential sets up the stage, but it itself doesn't play a role. What plays a role on the stage is quantum gravity fluctuation. Right. Again, it's not strictly QCD. It may inspire some new ideas for QCD, but not strictly the QCD yet. Okay. So right now we're considering 2 Wilson loops. Again, historically, Madassini, after he finished his 1 Wilson loop paper, right after that, he together with some other collaborators, they compute 2 Wilson loops. And of course, they can only find some power law decay in the separation of the 2 Wilson loops. And to have a mass gap, we expect some exponential decay. Okay, and we want to compute this one, and this is some ongoing work. Okay, the last example I want to show you is quasi-normal modes. Well, quasi-normal modes, as I said, this is eventually we want to see the real data. So the gravitational wave, usually a signal is like this. It has 3 phases, okay? So in spiral, merger, and ring down. So ring down part is sort of is a quasi-normal modes, okay? And of course, we want to compute the correction to the photo rings, but that's the next problem. So to compute the correction to the quasi-normal modes, we change the strategy a little bit. So we consider first fluctuating AdS2 metric. It can be obtained by dimension reducing the high dimensional arm black hole again. So we're going to have this A factor. The A factor has quantum fluctuation in it, okay? And then we consider the string Dyson equation, also mentioning Professor Gang Yang's talk. So this is, but we don't insert a Wilson loop. We just consider the equation motion, put in the quantum gravity average equals 0. This is a simplest version of the string Dyson equation. And again, we consider fluctuating background, so we have a factor here. But we can put this factor in the quantum average and use the Korean group, the one loop result for the quantum average of the 2-point function of the epsilon fluctuation. Okay, after quantum averaging, we have this expression for the correction factor. And this is just simply the quantum corrected version of the string Dyson equation, or the wave equation, just with the quantum corrected factor here. And effectively, the quasi-normal modes, we have a different potential, effective potential. The blue one is classical potential, and the red one is corrected. It's a little different. And we compute with the different parameters. Again, C times T, when C times T is infinity, is purely classical. When C times T equals 1 or smaller than 1, it's highly quantum. So you see, it's not, we don't need very highly quantum region, just a small perturbation regime, okay? We already see some correction to the poles, to the frequencies of the quasi-normal modes. So the blue dots is the classical one. So when we make C times T smaller, but not that small, still 10 to the power 4, we see some clear deviation, okay? So people claim they can compute quasi-normal modes very precisely, up to 5, 6 digits. We are suggesting, wait a second, slow down a little bit. Before you compute to up to 5, 6 digits, if you consider low temperature black hole, you probably want to include quantum correction first. And then you can compute up to 5, 6 digits. Because the correction is not small, maybe up to 10%. So 5, 6 digits accuracy up in the 10% error, it's nothing, okay? Okay, I think I finished the examples, but very brief, a few words about the ongoing work. So I think the J.T. Schwarzian story is nice, but I think we should pay more attention to high-dimensional version. I would call this AdS3 gravity, and the theory studied recently, restudied by Carl Jensen, is a high-dimensional version of J.T. Schwarzian. And the story is not new, but the revisited story. The story is we consider AdS3 Einstein gravity. It has infinitely many saddle points related by the modular transformations, okay? And we can rewrite it classically into a Chen-Simons theory, okay? And the new thing, or the new approach Carl Jensen used is to rewrite this Chen-Simons theory connection around a specific saddle. So let's say we can consider AdS3 saddle, we can consider BDZ saddle. You should ask which one you're more interested in, then you start with that saddle. With a given saddle, they can rewrite this connection explicitly using SL2R, different parameterization of SL2R. So they first get a WZW model and then move on to a Liouville-like theory. And using this Liouville-like theory, it's indeed play the role of Schwarzian theory, but one dimension higher. They can compute the quantum, well, they haven't, but we are planning, we are using their theory to compute quantum correction to D1, D5 black hole entropy, similar to Carl Jensen, similar to Iliesu Turaci, okay? And we are computing BDZ's quasi-normal modes correction. And another ongoing work is, as I said, I think the most physical one should be warped AdS3, and it should be a new dual theory. Okay, and fortunately, warped AdS3 is not a solution to Einstein Einstein theory. It's a solution to topological massive gravity. Unfortunately, people have written down the Chern-Simons form of topological massive gravity, and that's our starting point. And together with a student, I'm working on right now on the boundary theory of warped AdS3 gravity. If we can find that, to me, that's the most feasible one. Okay. So summary, I discussed lower dimensional AdS and its dual boundary theory in various dimensions. And of course, the most well-studied one is the JT and Schwarz duality. We use that to introduce quantum correction to a bunch of problems, okay? And we are using AdS3 and the dual theory, Liouville-like theory, but recently re-derived by Colin Jensen, to introduce quantum correction to some related problems. And we're studying new theories because eventually I have in mind is gravitational wave and photon ray. Okay, to introduce quantum correction to these problems, we definitely need new theory. Okay, and maybe also low dimensional de Sitter, because this talk is focusing on AdS. So probably de Sitter gravity also will play a role in some cosmology. And I think the good starting point is another paper by Maricina Turach and Yang. Okay, okay. Thank you much for your attention.
Questions?
Yeah. Right. Right. Mhm. That's a very good question. And I don't worry about that question. Some people may worry about that question because, as I said, my primary interest is high dimensional black hole. I go to near horizon, I only have specific saddle point. But for those people whose main interest is just lower dimensional AdS-FT, they have to consider a sample average of all the saddles, or even non-saddles. But for me, there's only one saddle because from dimensional reduction from high dimensional black hole to the near horizon region, I only have one saddle. That means I'm more conservative, or I have a little goal than what they have. I just study the quantum fluctuation around a specific saddle. But your question is very good. I know there's large community, the people they're interested in low dimensional AdS-FT. They need to consider all the saddles. Then they have trouble. They have hard time, very hard time. I'm asking simpler questions in some sense.
Yes, no, I wanted to understand, is it working? I wanted to understand better about the quasi-normal modes computation. So if I understood correctly, you said that there is a 10% correction from quantum correction to the quasi-normal mode, I don't know, frequencies. I mean, this sounds spectacular, but so as far as I know, when they observe gravitational wave experiments, the ring down shapes,
right?
They match very well with the classical GR simulations.
Right.
So, I mean, at which point do you think that this quantum correction should be
right?
observed?
That's another very good question. We consider that because my response is right now the gravitational waves they only consider, let's say, astrophysical black holes, either a few times or tens of solar masses, or the supermassive black hole is millions of solar masses. Indeed, our results turn out to be, if we consider a very large black hole, the correction is very, very small. We can never observe it. So what we consider here is primordial black holes. But that doesn't mean that we cannot observe the effects of primordial black holes. So we consider, let's say, from 1 kilogram to 100 kilogram primordial black holes. I asked some of my colleagues from studying astrophysics or cosmology, they said the quasi-normal modes of primordial black hole can also be observed indirectly, maybe in some CMB or in some cosmological observables. Yeah, we consider only primordial black holes. I agree with you. Yeah. Astrophysical black holes, forget it. No hope to observe.
Okay, another question. do we understand this quantum correction from the field theory side? So
If we understand, we go and book a ticket and get that 1 million prize. Yes, that's a good question. But I think we have some new ideas from gravity side. But in order to eventually understand what's going on the field theory side, we need to carefully translate that gravity insight onto the field theory side.
I think talked to me before this quantum correction like the metric activation. So can we understand like a graviton or something like that?
For sure, it's some, I would say, let's say Engels force BR-Mills, no confinement or no mass gap, forget it, right? It's at the origin. So I would make a bold guess. So that means if we consider some finite chemical potential deformation of Engels force BR-Mills, you open up a new part of phase space, which allows some new modes you never see in Engels force BR-Mills. That's my bold guess.
Thank you.
Okay.
Some small comment about the warped AdS.
Right.
You know, there's a simpler setup to get warped AdS. That's just you can just take this D1D file supergravity, and then warped AdS is just a solution to that. And there you have actually a continuous limit where you can interpret, like well, you turn on a parameter that you can get both the warped AdS solution and also ordinary BTC solution, and
Yeah.
you can also impose certain boundary conditions so that
Right.
even in AdS you can find this warped CFT, and in that setup we already found this so-called Carroll-Liouville gravity that has the symmetry of warped.
Right.
And then
Yeah.
there's also a symmetry breaking pattern discussed a few years ago with Yingfei Gu and other collaborators.
Okay.
Some comments.
Yeah, thank you much for the comments. I think you told me that before. But yeah, we're considering that. Maybe eventually, I don't know, we're working on it. Maybe, anyway, we are using a new approach. Maybe eventually we arrive at the old theory you found. But I would say this new derivation probably will still give us some insights, and it's easier to. Right. Let's say Colin Jensen, the theory is not new, but it gives us some new insight. Right. The similar way we are doing. I think probably eventually you probably will recover the theory you found, but it will give us some new insight, and which turns out might be easier to introduce quantum fluctuations. Or maybe already starting from your theory, it's enough. I don't know. Right. 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 But right. Well, we're trying to use a new approach to rederive that. Yeah. Thank you.
Okay. So maybe we can finish our session. Let's thank the speaker again.
Okay. Thank you.